All right, section 2.5. Section 2.5 is all about, um, as we mentioned previously, the word or, uh, signified by the union. Your book uses union. It kind of annoys me. I get it, but it still kind of annoys me. To me, it just makes sense. Listen, I'd be happy with this or this or this. What are you saying? You're saying there's a higher probability of this happening, clearly, because, this or this or this can happen. For instance, let's say 30% of women are blonde, and I don't know, 40% brunette. I'm just making this up. It's not going to work out right. I don't care. 25% black hair. So 5% red. And this is what they came from the factory with. So clearly, some are gray now. We're not worried about that. I don't care. Whatever. Listen, you're filling out the form. Listen, it could be black or red hair. Black or red hair. You'd be happy. Okay, cool. So if you reach into a hat, pulled out a name at random, what's the probability you get a black hair or red-haired person? Well, 30%. Okay. Notice that there is no overlap between black and red hair. Okay, you're black or you're red. That's all there is to it. There's no overlap. We call those, again, mutually exclusive. Okay, you can't be both at the same time. Well, that's cool. But what if so when you have that, the probability of A or B happening is equal to the probability of A plus the probability of B if A and B are mutually exclusive. Cool. Nice. That's not always true. For instance, suppose you had a situation like this. I don't know, black, brown, red, blonde, math, business, accounting. I don't know. I just made that up. What the heck? Oh, education. Good grief. Yeah, I don't know. We're just trying to make up some stuff people could major in, I guess. Bless me. Woo! We're going to talk about a couple things on this problem just because it makes me happy. Cool. First of all, if you look at it, does it look like the same percentage of red-haired people major in accounting as do black-haired people major in accounting? No, not even close. What we'd refer to that as when we see this kind of data, because this is real world data that I just totally made up, so don't worry about it. What we have here is we have what is called dependent relationship. Does that mean that if you're this color hair, you have to be a teacher? No, don't be ridiculous. It just means there is some sort of propensity there. 800. People get so offended sometimes. What do you mean? My hair color tells me what I have to do. Literally, no one said that, sir, ma'am. 150, 160, 220. And so if you add them all up, you should get, I don't know, 320, 410, 465, I think. One moment, please. There's 465 total people here. Notice that brown-haired people in accounting, you see, are mutually exclusive. But that's the only one that is. So if I asked you, hey, what's the probability that you get a brown-haired person and, or I'm sorry, not and, you idiot, or accountant, why, you would say, well, it's 55 out of, well, you could do it a couple ways. You could do 455 plus 130 out of 465. Or most books would teach you to write 555 out of 465, J, plus 130 out of 465. Which isn't that the same? It's literally the same, but it doesn't matter. That's how most books write it. Okay, so just get in the habit of thinking about it that way. Okay. Notice that while we're here, what is probably that you have brown hair and you are an accountant? Well, that doesn't happen, friend. It's 0. That's because they are mutually exclusive. Okay? But what if you said to someone, hey, what's probably you get a blonde-haired person or a math major? Nice. Well, I don't know. I feel like there are 100 math majors out of 465. I feel like there are also 130 blonde-haired people. However, if you circle this as your answer, you are dead wrong because you counted these 50 people how many times? Well, you counted twice, right? So what you'd have to do is, in theory, subtract them off for your final answer, which would be 180, 180, 180 out of 465. Okay. I personally think in a chart like this, it's easier just to add one way and then add the rest of them over. Okay, there's 100 plus 80 more done, but whatever. What you just did there is you said the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. This right there is the equation. I'll write it the way your book does just so you can see it. A and B, like so. But remember, note, I personally only ever remember this equation. Oh, shoot. This equation right here. And the reason for that is because I have too much stuff going on in my brain. I've got, birthdays. I got other crap going on. Wonderful sports things to remember. I don't know. Other things. What the square root of 2 is. I don't know. I got lots in my brain. I only remember this formula. I don't memorize just this portion of it. But what I do is I remember to myself this. If it's mutually exclusive, this piece here is always going to be what? If mutually exclusive, then this piece here equals 0. Okay? And so, to me, this is the way I always remember them when they're given to me in terms of a summation problem. Okay? Now, let's do a couple of examples here just for a good time. Ooh! Suppose in a senior college class of 500 students, 210 smoke. Oh, dear. 258 drink alcohol. Now, just take a wild stab. Do you think there's any overlap there? Yeah, probably. Alcohol. Nice. 216 eat between meals. Okay, eat snacks. All right, I guess. 122 smoke and drink. Interesting. 22 smoke and drink. Excellent. 83 snack and drink. 83 snack and drink. And I suppose some probably smoke and snack. Yep. And 52 do all three. And literally your book says, do all 3 bad habits. Whatever, dude. Whatever. Nice way to envision this is, of course, with a Venn diagram. Okay. So a person could do this, 52. That's cool. You got to be careful because those 52 people, this is smoke, drink, and I don't know, eat excessively, snack. What I'll put snack, I guess. Snack. Now, check this out. These 52 people snack. They also snack and drink. And they also snack and smoke. Are you with me? So be careful. 97 people smoke and snack. Well, that would be between here and here. Are you with me? It's 97. That means 45 people must be here and here. Does that make sense? Now, drink and snack is 83. Well, that means this must be 31. Okay. And then smoke and drink is 122. That means this is 70 right here. Now, a total of I don't know how many people smoke. 210, I guess. So I don't know. See what I got here. So I got 70 plus 52 plus 45 is 167. That means the rest of them, the other 43, only smoke. We can play the same game out here. What about the drinkers? There's 258 drinkers minus 70 minus 52 minus 31. 105 people only drink. And let's see here. What do we got here? We got 45. We got how many people snack? 216 snack. So 88 people here. Now remember, there should have been how many people in this building? There was 500 senior class students. When they're all done, this better add up to 500. So let's see if it does. 43 plus 70 plus 52 plus 45 plus 31 plus 88 plus 105. Oops, did I miss one? 43, 70, 52, 45, 31, 88, 105. Okay, something's a little screwy there. Oh, something's not screwy. Jay just doesn't pay attention to what he's doing. The other 66 people are boring. No, I don't know. They don't smoke, they don't drink, and they don't apparently snack, which clearly is on par with smoking and so forth. Okay, but whatever. These people don't do anything with the bunch. Okay, but let's say you reach into a hat. There's 500 people in this hat. What's the probability that you get a smoker or a snacker? Nice. Oh, well, I don't know. Literally, if you go 210 plus 216 is 426 people, you're wrong. Okay? You're absolutely dead wrong to do it that way. Okay? Now, once you have it listed out this way, it's quite easier to do it a different way. So I'm going to do it this way. Listen, the only people I'm not interested in are the people who just straight up drink and the people who straight up and don't do anything, because these are the only people that are that don't fit the bill. Everybody else in this picture up here, either smokes or snacks. Yes? But you could have done it this way. You could have gone, well, let's see, there's 216 over 210 over 500 plus 216 over 500 minus, now let's see, who do we count twice? Well, we counted these guys twice, so that'd be 97 out of 500. So regardless of how I get here, hippie, I would get 329 out of 500. Or I can come up here and go, hey, look, what is 500 minus that? I don't know. It's the same. How about that? All right, how about that? So kind of cool question, kind of a nice, easy way to do it. What you'll find in this section is a lot, and I mean a lot, of situations where it's either given in a format like this. Okay, if it's a situation like this, I'm gonna make myself a Venn diagram every time. I just think it makes my life easier. So I will model another of those perhaps. Oh, let's see what we got over here. Yeah, so here we go. The automobile manufacturer concerned about a recall of a best-selling four-door sedan. There was a recall. 25% chance at the brake system, 25% chance of brake problems. It is 18% transmission. It is 17% fuel system. And 40% in some other area. 40% other. Now, let's see what that adds up to. That's 65 and 35 is 100%. Boom. So what does that tell me? Okay, well that tells me then that these guys are all mutually exclusive, yes? So what's probability it's the brakes or fuel, okay? Okay, let me back it up. So let's just say probability So the way it's written, the way it is written here, this is 25 plus 35 is 60%, plus 40 is 100%. So based on the way it's written, these guys are mutually exclusive. Now, if I do this here, it's kind of a situation, okay? What's probably the defects are in either the brakes or the fueling system, okay? Let's see, that back up. Part A. What's the probability that the defect is in the brakes or the fueling system if the probability that's in both is 0.15, okay? So in other words, what they're telling you is this. They're telling you this, which makes no sense. I mean, brakes and fuel. By the way, weird combo. Okay, but if that were true, then you would go 0.25 plus 0.17 minus 0.15 equals 0.27, yes? Now, it says this. What if there are no defects in either the brake? What's the probability that the defects are not in either the brakes or the fueling system? So if it's 27% that it is, then the what do we call that? The complement of that is 73% chance that it's not in either the brakes or the fuel system going forward. Now, I didn't like that problem because it should have had a deal where all the probabilities add up to more than 100%. And if it did add up to more than 100%, why then we would say, well, clearly then there has to be overload. For instance, there has to be overlap. For instance, on the previous one, right here, where did it go? Right here, these clearly add up to more than 500 students. Clearly, okay? So that means there has to be overlap. And so that kind of bugs me the way that problem was written. I don't really care for it much. Ooh, here's a cool one. Here's the shift that they work. And so you got day, evening, graveyard is what it says, sure. And then unsafe conditions and human error. Nice. So 5, 6, 2%. 5, 6, 2. Human error, 30, 25, 32. That's what the picture looks like. Okay, so it says this. Accidents can occur, blah, 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 yada, yada. If the accident is selected randomly from 300 reports, what's the probability that the accident occurred on the graveyard shift? Okay, now let's add these up just for a good time here. Let's see what this all adds up to. What are you thinking right off the bat? 32 plus 25 plus 30 plus 5 plus, that's times, dummy, plus 6 plus 2 is 100%. Yay! So what's the probability that we got a graveyard accident? 32%. Okay, what's the probability that we got an accident occurred due to human error? Human error. 62, 87. 87%. Nice. What's the probability that it occurred due to unsafe conditions? Well, listen, if it was either human error or unsafe, that means 13 has to be the probability of unsafe, because another way of saying unsafe in this case is not human error, right? And what's probably the accident occurred either evening or graveyard? Evening or graveyard. Now, if you think about that one, are those two mutually exclusive? Well, yeah, they're on parallel tracks, yes? So, you can do it a couple of ways. You can add all four of those up. Maybe that's too much work for you. For me, that's too much work, for heaven's sakes. I realize that there's 37%, if that makes sense, that are not what I'm interested in. So the other 63% then, that makes sense, must come from the part that I'm interested in. And in fact, it does. How about this? What's probability that it is evening or unsafe? Now, these guys are not mutually exclusive. How do I know that? Because here's evening, here's unsafe. They clearly overlap one another. So you can add it up any way you like. If you do this, you got this is 31, 36, that's 38%. Nice. That's it. That is section 2.4. It's quite straightforward. I don't think you'll have any trouble with that. 2.5 rather. Section 2.5? Come on, Jay. Pull your head out. Yes, that was, sorry. So that was section 2.5. So just make sure that you get that done. It's pretty straightforward. It's probably the easiest section of the bunch. Section 2.6 I'm going to do in its own video.